Hi everyone, welcome back. Today we will have our last hands-on session for your 2D finite elements project, and it will be on post-processing. So here I have the same runner file we did before in our previous sessions, and at the very end I've just added a post-process function, so nothing is new here. And let's see what the post-process function does. So let me run this. And okay, now you should see the plots. So we have different stresses, strains and displacements, and we are plotting them throughout our domain. So that is the purpose of our post-process function. So let's actually start discussing what we do. So as you remember, we had taken a look at these two types of elements in our previous sessions, and for the constant strain triangle we have 1 Gauss point, and for the bilinear quadrilateral element we had 4 Gauss points. So what we want to do is we have our displacement values, right? We have calculated them and they are stored in our extended node list. So using the values of the displacements, we want to calculate the strains and stresses of these elements. But what do I mean by stresses and strains of an element? So for the triangular element with the single Gauss point, we will calculate the stresses and strains at that Gauss point. Okay, so we will have throughout the element for different types of stresses and strains one constant value, and for the four-noded element we will have 4 different stresses and strains calculated at for each different Gauss point. And we should plot these stresses and strains on these Gauss points. However, to my knowledge, we are not really able to do that in MATLAB. So what we will do instead is plot the values calculated for the Gauss points on nodes instead, so like this. Okay, so we have that issue for stresses and strains, but we don't have that issue for displacements. Why? Because we have the different displacements of different nodes at hand already in our extended node list. So naturally, since we have 4 different values for the different nodes for the stresses and strains, in the 4-noded element, these values will vary along the element. So we will not see a constant color inside the element. So if we go back to our figures, so for example, stress yx, if we zoom in here, you will see that inside an element, the stress is varying, right? It varies from somewhere along 0 and 0.1. And it's actually more obvious in the strain YY plot. So if we go here, for example, we can see that they are varying. Okay, so that's one thing we will need to be mindful of when we're doing the post-processing. So let's go to the post-process function now and see what we have. So here we have a, I mean, it looks long, but actually quite straightforward function here, the post-process function. But inside we call on our element post-process, which actually which actually gives us a stress, strain, and displacement values for the whole domain, element by element. So this part is just for plotting. In this element post-process part, we actually calculate the stresses and strains. So before we come to that, as usual, we have our PD and PE, number of nodes, number of elements defined, and we have a scale. So remember, in your first project, we had a magnifier for the deformation in the post-processing part. This is the exact same thing. So if our displacements are small, in order to see the deformation better, we have a scale to magnify the deformation, and we'll see how we use that. So first, let's go into our element post-process and see how we calculate the stresses and strains and displacements. So should be here, yes, element post-process. So again, we have our node list, element list, and extended node list. And we start by the usual initializations. And we have an if condition. This is again nothing new. If our node per element is 3, our Gauss points is 1. And if our node per element is 4, our Gauss points is 4. And for the types of elements you are expected to have in your project, you will need to add new if conditions here. So now we start by initializing the displacement, stress, and strain matrices. So let's take a look at displacement first. So for number of elements, so for every element, we have node per element. So for every element, we have nodes of that element. And for every node, we have PD. So PD is our problem dimension is 2, right? So because displacement is it's a vector, right? It's a two-dimensional vector. So it has two x and y components. So that's why for every element we have a corresponding corresponding nodes, and for every node we have PD. Let's say values for our displacements. And this one here, I mean, this is same as not writing one. If we didn't write one here, we would have the same thing. It's just we have that so that it looks similar to our stresses and strain. Okay. So for stress, we have again a number of elements. So for every element, now we will take a look at our Gauss per element, right? So we're calculating the stresses and strains at the Gauss points, remember? So that's why instead of node per element, we have Gauss per element here. And as you know, stress and strain, they are both two second order tensors. So PD times PD, 2 by 2, right? That's why we have PD here. So for every element, we look at a specific Gauss point, and then for that Gauss point, we have a second order tensor corresponding to the stress and the second order tensor corresponding to the strain. And these tensors are actually 2 by 2 matrices in this code. So yeah, so we can actually start now. So we have a for loop over the number of elements because, well, we have number of elements here, right? We will calculate these things for every element separately. So, and E, it stands for the element we are looking at. So now we have our small NL, and this is again something we have encountered before. It stores the information of the nodes, node numbers of the specific element. So element list, we are looking at the E element and want to node per element. So this stores the nodes of the element. So let's actually start by filling out our displacement. So we don't have to calculate anything because we have calculated our displacements already and written them in our extended node list, right? So remember, the 4 times PD takes us to the displacement columns plus J, so it's either 1 or 2, so X displacement or Y displacement, right? So we have 2 for loops, node per element, and PD. So again, remember we're inside a for loop over E, so we're at displacement, we are now writing the values for the E element, as this was number of elements. So I, it should be the specific node, one of the specific nodes of that element, and it's a loop over the nodes per element, so that also fits. And then J, it's either 1 or 2, right? It's PD. So J and comma 1. It should be equal to whatever displacement we have for that specific node. So we are inside the ith node of NL, right? So NLI takes us to the node number in the extended node list. So we put it here, and then we have 4 times PD plus J, which takes us to our displacement. Okay, so next, what we want to do is we want to calculate our strain. And using the strain, we want to calculate the stress then. So as you know, stress is just the double contraction of our constitutive tensor with the strain. And this is quite straightforward. This will be just 1 line of code. So in order to have the stress, we will first calculate our strain. And it's a tad more complicated, but as you will see now, we have most of the things we had calculated already in our in the first video. So that will not be very hard either. So let's see, for the strain, what we have is actually the symmetric gradient of U. So U is our displacement vector, and the symmetric gradient of U is our strain. So this is what we have here. But the thing is, what we have as U is just values for specific nodes, right? So for every node we have a displacement value. So the gradient of a scalar number, I mean, it doesn't change, right? So it should be 0. So we can't actually take the gradient of these. So what we do is, similar to the first video, we have our shape functions, and we approximate the values of the displacement along the element, the whole element. So such that we don't have just the nodes, but an expression for the whole element. So what we do is we use our shape functions. So this UI, I stands for the node. So for every node we have a summation over NU, and as you know, it's the Einstein summation convention. So now we have an expression for U that we can actually take the gradient of, and that gradient is grad NI diad UI, and the second term with the gradient of UI is, well, 0, as it's this scalar, and we are left with this expression. And what's nice about it is that this thing is nothing new. So this is the inverse transpose of the Jacobian, and this gradient of the shape function in the natural space. So this is the gradient of the shape function in the physical space, right? And we actually had that before. In our first video, this expression we have here, we had called it grad in the code, remember? So let's actually go to stiffness. And yes, so we calculate our J. Well, we calculate our J here. We calculate our natural gradient of N here. And then we say that the inverse transpose of J times grad net is grad. And what we called grad is, well, this thing. Okay, so from the stiffness function, and inside that we had the grad and net function, we had Gauss point and our constitutive delta. Using those, we actually have the expression for this now. And what's left to do is to take the dyadic of that thing with the displacement of every node. So again, I. So we have a summation over the node, okay? And I'm sure you have seen it already, but let's just go over it. The dyadic operation works like this. So if you have a dyad with two vectors, it will give you a tensor, a 2 by 2 a second order tensor. And it will be like this. So AI bj will be placed at aij. So you can think of I and j as placeholders. And we will need to call the dyad function. And once we call the dyad function, remember we have this. We also have this. We have the displacements. We just have to write them in a specific way, such that we can have the dyad operation, and that will give us the gradient of u. And the gradient transpose of u is, well, the transpose of this, right? And the transpose of this dyadic is, well, B dyad A. So what we will need to do to calculate this is to plug in our dyad function ui dyad nix, okay? And we will then be able to calculate our strain. So let's see how we do that. Well, first, to do anything, we first need the u, right? So, first we start with our coordinates. So we need the coordinates of the nodes. And then specifically we need to have them as column vectors. So these lines here should be quite familiar to you. We did them before. So we first have x as so this x here, it's in the form of row vectors, right? So we have node per element, rows, and PD columns. So for every node, for every row, we store the, let's say, the coordinate information of the specific node, okay? So we first write that, so from 1 to node per element and 1 to PD, our xij, so I is our node, j is our direction, is in our node list, the ith node of NL inside the node list, and its jth coordinate, okay? So, and to have it in the form of column vectors, we take its transpose, okay? And then we need to have our displacement values we had calculated in the extended node list in the same form as core, so again as column vectors. So now we have PD times MPE 0, so for every column we will store the different values of different coordinates of different nodes. So for column 1 should store the coordinates of the first node of the element, okay? And the first row of first column is the x coordinate of the first node, and the second row of the first column is the second coordinate or y coordinate of the first node, okay? So sorry, but we want to do that not for coordinates. So what we have in core is that, the thing I described. But for u, we want to have that same thing in terms of displacements. So you'll see that we have the same loop. Well, This time I again from NPE and J from 1 to PD, but this time we write UJ comma I instead of I comma J, because we, instead of taking the inverse later, we just write it properly here. We take the ith node of the element and its corresponding displacement. Okay, so now we have displacements as column vectors stored in U. Let me actually show you how we plot the different the different stress and strain values for elements, such that you'll see why we are using column vectors here. Okay, so let me open a new script here, and okay, so we will use the patch function, and I'm sure some of you are familiar with patch from the first project, because I know some groups use the patch function to plot their boundary conditions, so the triangles and the arrows. So it's that function. So what patch does is it takes the coordinates of a polygon. So you have a polygon, like for example you have a square, and it takes in the x coordinates of every node as a column vector, and then the y coordinates of every node in the same order as a column vector again, and plots the polygon with as a filled shape. So to vary the color inside of it, you just as we wrote column vectors for the coordinates, you also write column vectors for colors, so corresponding to every node. You write a value, and that will in turn vary the color inside the patch. So let me show you what I'm talking about. So let's have our x coordinates, and our y coordinates, and our colors. So let me delete this, and in turn we'll have patch x, y, c. Okay, so let's see. For the three-noded triangular element, we will have three different nodes, right? So let's start writing the x coordinates. So this should be 0, this is 1, this is 0. So 0, 1, 0. See, as a column vector. And y coordinates is 0, 0, 1. So 0, 0, 1. Okay. And the color is, well, for the triangular element, as I said, since we are plotting the value of the single Gauss point, they won't have a variation of color, so we can just enter the same number 3 times. Okay, and actually I think we used patch to plot the stresses too in the first video, if I'm not mistaken. I'm not sure, but in that we had also no variation of color, but I'm not 100% sure, so you can, if you wonder, you can just go back and check. And so let me just clear the figures we had here, well, the one, and then just run this. And let's see what we have. Okay, so we have a triangle here, and it's a solid color, right? So now let's see what happens if we have our 4-noded element. So this node is missing, right? So let's add it there. So x coordinate of that node is 1, and its y coordinate is, and by the way, these are wrong. This should have been yeah, like this, and this should be 1 now. And so for the square element, or the four-noded element, let's have a variation of colors. So 0.1, 1, 3, 0.4 maybe. Okay, and again, let's do CLF and run this now. Okay, now see that we have a four-noded element and we have a color variation. So on this node, well, let me also plot a color bar here. So yeah, this is better. So on the first node, it's something around 0.4, it should be, and well, it's 0.1. Well, sorry, yeah, this is 1, 0.5, this should be around something 0, so 0.1, yes. And so the second node we had is this, and it's something around 1, right? And it is actually 1. And the third node, it should be 3, it is 3, and the fourth node, it's some blue around here, and that is 0.4. Okay, so that's how patch works. And because we want to use patch, we use this format. So we write them as column vectors, okay? That's why we do that. And now we can move on to the calculation of our strain, so epsilon. So we have a for loop over the Gauss points. And so this is similar to our stiffness, right? In that we also had a for loop over the Gauss points. And we initialize our epsilon, so it's zeros PD by PD. As I said before, it's a second order tensor and our problem dimension is 2, so it should be 2 by 2. And then we have a for loop over the nodes per element. And we can actually start the calculations. So if you check the stiffness function, you'll see that they are exactly the same. So J grad Gauss point grad nat, and again J, and lastly the grad. So these parts are exactly the same. And down here we have our grad nat function pasted, our Gauss points function pasted, our constitutive delta pasted. Okay, so we have everything we need. Sorry, I went too far. Okay, we were here. So again, we calculate our Gauss point values, so Xi, eta, and alpha. And using that, we calculate our grad natural, so this thing. And using that, we calculate our Jacobian. Nothing new here, like what we did in the first video. And using the Jacobian and the natural gradient of n, we have the now what we called grad here, so ni comma x. Okay, so then what is left to do is just calculate this. So epsilon is equal to itself plus, so we are over a loop and we should be adding, right? And maybe I didn't explain it very nicely, but so these grad u and grad transpose u, these are something like ni, these are something ni and ui dyad. So we have a summation over I. Okay, so we should be summing this up over I, which corresponds to our number of nodes, right? So that's why we have a loop over node per element. Okay, and so what we do is we just write it here. So 1 over 2 dyad So the first argument of dyad is for the gradient of u, which should be what we had at grad. And the second argument is u plus, again, dyad. This time it's the grad transpose, so they should switch places now. It's u comma grad. And what happens here is, remember, these are all column vectors, so u and grad. So for u, if we are looking at the ith column, we are looking at the ith, let's say, node. Okay. So again, remember, I is from 1 to node per element. And similarly, that it's the same thing for grad. So that I you see here is the I we have here, okay, in this form. So that is basically what we have. And we have this here because we want to have every value for that specific node, right? So we just calculate that and add it to itself as it's a summation over I. And that's how we calculate our epsilon. And once we have our epsilon, and remember, we are doing this for every Gauss point. Okay? So for the triangular element, we do it for just one Gauss point. For the four-noded element, we do it for every Gauss point. And that's why we have a loop over 1 to Gauss points. Okay? So we are inside the loop over the number of elements. So we are looking at every element one by one. And inside every element, we are looking at every Gauss point. Okay? And for every Gauss point, we need the information of every node. And we have a summation over them. Okay. So the thing left to calculate is our sigma. So we first initialize it. It's the same thing as our epsilon, as it's a second order tensor again. And the calculation of sigma is pretty straightforward, so it's just this. So it is quite similar to what we had for our stiffness calculation, if you remember. So we have a loop over A, B, C, and D, and they all go up to PD. And sigma AB is, again, this is a summation, so it's equal to sigma AB plus constitutive ABCD times epsilon CD. So this is the double contraction we have. So IJKL, ABCD, KL, CD. Okay, that's pretty straightforward. And lastly, we need to write the epsilon and sigma values inside our strain and stress matrices. So remember, what we have calculated here is we are inside this loop over the number of elements. So we are calculating the sigma and the epsilon of a specific element. So we should store this element-wise information inside a global strain and stress matrices, okay? So again, we have two loops over A and B, and remember, we're still in the loops over the elements and the Gauss points. So GP and E. So if we go up, remember that our stress and strain were in this format. So for every element, we look at a specific Gauss point, and for every Gauss point, we have a strain tensor 2 by 2 and a strain tensor here and the stress tensor here. Okay, and what we do is, for the E element and for the GP Gauss point of that particular element, we write the A to B value of epsilon to the A to B index of strain, and we do that same thing for sigma. Okay, that is quite straightforward, I think. And as I said, there is nothing new here except for the dyad function, which just takes I don't remember if I've talked about this, so let me just go over it again. So the diet function does this, right? So aij, aibj. So let me actually change these to a and b. So our PD is 2, a is zeros PD by PD, we know that. And these should be now a and b. So this here is exactly what you see here. So take the AI value, take the I value of A and multiply it with the J value of B, and then write it to the place A, I comma J. That's it. So that is our diet function. So we're done with the element post process. So it means that we now have every displacement, strain, and stress value we need. So what's left to do is actually plot them. So let's see how we do that. Well, first of all, the stress and strain, they are 2 by 2 tensors, right? And we can't really plot them, so we need to plot different elements of these tensors. So here we have, for example, strain yx, or let's say stress yy, stress xx, stress yx. So stress xx is the 1-to-1 value of the stress matrix, right? And stress yy is at 2-to-2 and such. Okay, so we need to extract those and then plot them separately. So what we do is first we have a switch over the nodes per element, because for the 3-noded one, we have one Gauss point. So the value we have for every node should be the same for the stress and strain. But for the 4-noded one, we will have different values. So that's why we have a switch here. And if our node per element is 3, we do something. And then if our node per element is 4, we do something, well, again, similar, but not quite the same. So let's see what we do. So we have a for loop over the number of elements. And again, we need the information of, well, remember for patch, we need the x and y coordinates, right? So in order to have that, we again use our small nl. So small nl stores the, the nodes of the specific element, and then using the small nl, we now want to calculate the deformed coordinates of the nodes. Okay, so what we have here is the undeformed coordinates, and here we add to that our displacement. Okay, so we do that for x and y. So let's see how we do that. But first I want to show you something else. So patch, we have seen how it plots for an element, but what if we have 2 elements? So it's actually quite simple. So we know that we have for a specific domain, we have one type of element, right? So for example, if our domain is made up of 4-noded elements, the second element will also have 4 nodes. So if we write the nodes of the second element, the coordinates of the nodes in that same order, so so this element was at 0, 0 to 0 and 1 to 1, right? So the next one, it should be, its x coordinate should be at 1. The first node of the x coordinate should be at 1. And the second node, the x coordinate of the second node should be at 2. The third node should be at 2 again. And the fourth node should be at 1. And the y coordinates should be the same. So let me just write them. 1 and 1. Okay. And similarly, we need to write the different color values here now in the same order. So let's have, I don't know, something like 0.3. here 1.5, 2, 1. Okay, and let's clear the figure again and run this. So let's see. Okay, this is the figure we have. So we have two elements side by side now, and remember this is the same as the first one I had plotted, and now we have a new one varying with these new values I have added. Okay, so we want to do this for all of the domain now. So let me go back to our post process, and now we can begin with writing our x and y coordinates. So what we do is we just write these, okay, in this format for the whole, well, for every element now, element by element. So for we have a loop over I, the number of elements, and then j, the number of nodes per element. So the jth node of the ith element, again it's reversed because of the column situation. We have enl, the jth element of the jth node of the element 1, so the x coordinate in the enl plus scale times, so scale was our magnifier, remember, the displacement we had, so again the jth element we're looking at, each time 4pd plus 1, so this takes us to the x displacement. And we have the same thing for y, and the only thing changes is these ones become 2. Okay, so we have our for a element for the element we are at, we have written the now deformed coordinates of x and y, and we do that for every I. So I is columns, right? So like this, we add the different coordinates of the different nodes. Okay, so let me actually close this, and we have our x and y coordinates now. What's left to do is to in the patch function we need our color value, right? And our color values will be our different stresses and strains. So what's left to do is extract those from the big stress and strain values matrices. So again we have, remember we're looking at the 3-noded element. So in this case, the stress we have for the ith node, so the ith element, so I is from 1 to number of elements, the 1-to-1 let's say element of that stress is our stress xx, right? So 1-to-1 is xx, 1-to-2 is xy, 2-to-1 is yx, and 2-to-2 is yy. This is, I think you all know this. And so j is our node. So the jth node of the ith element, the stress xx, we're writing the stress of the ith element. And we can do that because the stress of the ith element is just one value. It's what we calculate on this Gauss point. We can do that for the 4-noded one. That's why we have a case. Okay, so let me repeat. The stress of the ith element, the jth node, it should be what we calculated as a stress of the ith element. Okay, so we repeat this for every different stress type. So xy is, again I said 1, 2, yx 2, 1, yy 2, 2. And for the strain we have the exact same thing. So you can just copy this and replace the stresses with strains. You will get the correct values. So it's not something new here. And lastly, for displacements, now we have different values for different nodes, right? Because displacements, they are not connected to the Gauss points. They are we had the displacement values before that. We have them extracted from our extended node list. So what we do is, again, for the ith element jth node, we take the, again, ith element j node 1 to 1 is our x displacement, and if this one becomes 2, it becomes our y displacement. Okay, so remember our displacement was like this. So PD, comma 1, this doesn't change, and PD is just our direction. So now we have our displacement values as well for the 3-noded element. And let's move on to the 4-noded one. So up to here, everything is the same as we had before. And now we have something different. So now we have 4 different Gauss points, and we should write the value of the specific Gauss point to each node, okay? So again, we have our loop over the number of elements and our loop over the nodes per elements. Now, what we had before in the 3-noded one, this thing, let me paste it here so that you can see that. We call it value. Okay. So, and the difference is here the column stands for every value of this index, right? But if we take a look at the format of the stress, again, if you go down, it's number of elements, Gauss points per element, PD. So if this is a column, for the triangular element, we already have just one value for this. Okay? So because we have one Gauss point, our Gauss per element is 1. So it doesn't really mean anything. That column, it just takes whatever value that corresponds to that. Okay? But for the 4-noded one, now this stress column, this is not just one value. This is actually 4 values for the different Gauss points. Okay? So because of that, we first take those 4 values and store them and call them value. And then for every node, so j is from 1 to node per element, we write the corresponding value of the stress. So the ith element jth node, the jth Gauss point value, okay? So this is the difference between the third and the 3-noded one and the 4-noded one. And you can see that the only thing that changes is for xy, this becomes 1, 2, again yx 2, 1, yy 2, 2. And we have the same thing for the strains. And our displacements, now because our displacements didn't depend on the Gauss points, they're just what we had in the 3-noded one. Okay, so they're the same. And now we are actually pretty much done. What's left is just to plot them. So we want to plot 10 different figures. So we have the same, let's say, plotting function 10 times. And what we have here is our good old patch. So x, y, now we want to plot stress xx. So it's what we write in our color, in the place of our color, and phase color interp. And our color map, we set it to jet. And we just add the title, distribution of stress xx, our axis equal, and color bar. And we copy this and paste it and change the stress types and the titles. And then stresses become strains. And lastly, the displacement x and displacement y. And in the very end, to not have them on top of each other, we say move GUY. So F1 is the first figure, we move it to northwest, so the left top corner, and etc. Okay, so let me actually close all, and let's run this again and see our end result. So let me okay, so this is what we have, and as you can see, we have a variation of stress inside the element, and similarly for the strain. And if you take a look at displacement, well, they also do vary. However, it's not because we have more than one Gauss points, it's just we have the displacement values of different nodes. Okay, so you will see the same variation in the triangular element for the displacements, but for the stresses and strains, you won't see a variation inside the elements. So let me actually run a triangular one. So run this. Well, I think there's a problem. So let me close all and run it again. So let me take this, and okay, now we see them properly. Because we were plotting on the existing one, I didn't want to close all of them because then I need to move the windows and stuff. But yeah, so as you can see, there is no distribution of stress along along the specific elements, and the same is for the strain. So they're just solid colors. But if you look at the displacements, they all have the same variation because, well, as I said before, it doesn't depend on the Gauss points, it depends on the nodes. So yeah, so that's it. So this is the end of our hands-on sessions. I won't show you how to do the GUI in the GUI, but I think you don't need it now. You have learned how to build a graphical user interface in your first project, I think. So you can just take a look at the project description, and yeah, that should be enough for you, I think. So I hope this was helpful. I hope you liked the videos, and if you have any questions, you can always reach me via email. So thank you for watching my videos.